Welcome back from the break. Now we're ready to jump into some energy storages in the electrified vehicles. We will look at batteries and supercapacitors. When we're modeling batteries, we are in the QSS framework. We have the power requirement that is coming from the cycle and from the electric machine, and it might be need for power output, or it might be regenerative power coming in. And it goes into this power amplifier that is essentially a converter that takes the electric power in, and depending on the voltage that the battery has, it goes into and gives a current that depends on the current state of the battery. And the models for this have, the model for a battery has three components. We have the first part here, which is the power electronics, that does the conversion from input power to a current that will go either out of the battery or into the battery, depending on if we are consuming or if we're doing regenerative braking. Then inside here we have two models. One is the connection between the state of charge and the voltage. So depending on the state of charge, we have a terminal voltage of the battery, the voltage that we're seeing out of the battery. And that voltage will depend on the state of charge, and it will depend on the current, and we'll see an explanation of that on the next slide. And then we come to the state of charge, which is the charge level. So Q is the integration of the current, so we're integrating the current to get how much charge the battery has internally, if we have pulled out more or if we have put in more current over time. And the state of charge then is related. The state of charge is the relation between the current status and the maximum current that we have. So looking to this relation here that has both state of charge and current, we can make this type of experiment where we at time 0 we start to pull out a certain current, I2, and this I2 is small here, it's bigger, and it's the biggest here. And then we start to monitor what is happening with the voltage out of the battery. So first there is an activation part, and then the voltage starts to drop. So with small current we get a smaller drop, and higher current we get faster drop and faster drop. And the two effects that we're seeing are related to the resistive losses that we have here. So higher resistive losses are expressed by the differences between these lines here. So it's this part here. And when we are using a low current and a high current, the high current drains the battery quicker. So we see that this change here gives a steeper voltage ramp. So this is the starting point for modeling batteries when we would like to just keep track of it. If we want to do more details, investigations, and keep track of the battery state in more detail, then we might need to go up in more advanced models. And this is then some models and equivalent circuits to the capacity of the battery. So this one is the ideal model that we are used from high school physics and high school electronics, where we have an ideal voltage source. Then the one that we're using mostly here is that we have an ideal voltage source that has its dependence, the voltage dependence depends on the state of charge, and then we have an inner resistance to capture that we are losing power, that we are losing energy when we are extracting high currents. And then we can do more advanced models to capture more dynamic phenomena and extend it also with inductances in the system, and then we have even more advanced models. And in the end, we can also look at the physics and look at the things that are happening and model the physics with differential equations for each part, and model the diffusion of electrons and diffusion of ions in the different materials here. And with that, we can see that these react with some properties that are similar to the electric equivalent models. So from the physics we can get approximations in the equivalent models, but we cannot do the other way around, that we can get the electric equivalents from some experiments and then infer backwards to what it is. We need this coupling between the physics and this thing here to see what are the effects really a result from. So different chemistries have different voltage responses, and we will look at 3 different batteries that are, 2 of them are fairly similar, while the third will be a bit different. So here are 2. We have this LFP battery, and then we have this A123 battery. And if you're looking here at the voltage behavior, here we're not looking at time, but we're looking at ampere hours that we're taking out. So we have like full, we're taking out everything here, so it's related to one is the full capacity of the battery. And we are using the 3 batteries, but we're making the same experiments with them. So we're making one experiment at 6 ampere for both batteries, one here, one here. Then we're making an experiment with 12 amperes and here and there. So this is 6 amperes, these 2 are 12 ampere, and this one is 18 ampere. And we can see that the voltage for the A123 battery is the voltage characteristics of the A123 battery is pretty flat. While for the other one it's also pretty flat in the beginning, but then it drops more than the A123 battery. So this shows one thing that is interesting and that will be used later, and that is that the voltage is fairly independent of the state of charge. That will be a little bit of help in the control theory development when we look at optimal controllers. And then we see it's a little bit troublesome because we don't know, we cannot just look at the voltage to pull a conclusion of whether it's fully charged, whether it's charged, or whether it's close to become depleted. So this is a challenge for what is called state of charge estimation. While it's easier with the LFP battery here. For these 3, we see that there's a bigger relation here. There's a bigger connection between the state of charge and the output voltage. But here we can see the difference between the lines here. For a battery, we see a reflection of the inner resistance as we have the different currents here. And we also see the characteristics with the drop in voltage as function of discharged energy, or lowered charge inside, or lowered charge inside the battery. So the third cell here is from Alelion, where we see a reflection of a discharge cycle that goes down here, and then it turns over to a charging cycle, and then it goes back here. So it cycles over one deep charge and one deep discharge, and then up, and then it does several shallow charges, several shallow discharges and recharges. And when the battery ages, the capacity is decreasing, and we can follow this decrease by monitoring the amount of energy that we have here as the time goes by. And in battery nomenclature, 80% reduction from the new cell. We have new cell capacity here, but an 80% reduction, which would be about here. That means end of life of the battery. I have put end of life here at 60% just to get a big separation between the curves, but you can see how the battery changes with the aging of the cell. We have aging in several ways. We have calendar aging. The cell is aging while it's just sitting there. And then we have cycle aging, and we can also do more stressful aging of the cells by running them under conditions that the battery doesn't like. Another thing that we need to look at here is to monitor the state of charge. And if we just would do Coulomb counting, that is, we're measuring the current and we're counting the energy, or we're counting the charge that is going into and out of the battery. If we just do that, the battery will drift. And this is an example here. The top one, we're doing reset after each cycle is completed. And we start always here in the charging down, and then when we come back up here, we have needed to put in more electrons than what we took out. And if we do some computations here, we, for these, lost 2 times 10 to the power of 20 electrons per cycle. That doesn't mean that we lost them. They didn't disappear. It's that they just didn't do any useful work over the cycle. And this shows how the drift influences over the cycles that were measured. So here we just integrated the current into and out and not bothered about making the reset, just integrating. So this is Coulomb counting, gives rise to this. But then with some intelligent means we need to couple it to the voltage also. So this becomes an important part in monitoring the state of charge. So for your modeling, we will suggest that you're using a model that is of this structure. So we have an open circuit voltage that depends on the state of charge, and then we have an inner resistance part that influences the losses that we get when we take power out and we put power into the battery. And this type of model is frequently used to determine the power limits, and is used in the battery management system to estimate, for example, the state of power and also other parameters. So in the battery management system, the BMS, we are monitoring the voltage, we're monitoring the current, we're monitoring the temperature, and we're monitoring the state of charge, the state of health. So the state of health is related to how much energy we can have in it, for example, or state of health is not clearly defined, but a collection of different things. And and it's the BMS manufacturer or BMS programmer that determines what's the state of health, how it's defined. But when the battery ages, you saw that the capacity decreased, and at the same time the inner resistance can also increase. So we need to keep track of the state of power. That is, how much power can the battery deliver and how much power can it take up if we are doing a regenerative braking. And we have also the maximum charge current and maximum discharge current that is monitored by the battery management system. Supercapacitors are like a special case of the batteries where we have a capability to deliver much more power at short time instances, but they are not energy optimized. So they can be used to do load leveling of the battery, and they are very similar to batteries in their modeling. So we have a storage here where we have a voltage that depends on the state of charge Q. So this is the connection between the voltage and the charge Q here, where we have the capacitance of the capacitor. And the Q here is the integration of the current like we had for the battery. So this is a core part in understanding the capacitor and using supercapacitors and ultracapacitors in the system. So now we have talked about the mechanical parts and we have talked about the electrical parts. But to get all these systems to work together, we need to be able to transfer power back and forth. So we have electrical power links, we have mechanical power links, and we have gearboxes that we are using to match speeds so that they are going into the right domain and right operation region for different components. So, power links. The battery is a DC component, and we can also have several battery packs that can have a different state of charge. The grid that we're using to charge the vehicle is an AC system, so these are incompatible. We cannot just connect them to each other, so we need electrical glue components. In the vehicle we need DC-DC converters. For example, if we have a fuel cell vehicle or if we have a vehicle with different battery packs, or we have battery packs and supercapacitors, DC-DC converters are necessary. And then for controlling motors, we have inverters that are used to take the DC from the battery and give an AC out to the motor controller. So these are devices that control the AC machines. And finally we have the inverters connected to the grid if we are charging the vehicle with AC, and then we need an AC to DC converter inside the system. But we could also think of having the AC to DC converter outside the vehicle if we have a DC charging standard. Or if we're going for a DC charging in the standards. The modeling of the power link is essentially done by model the power transfer and the power losses, and we use Willens-like models. Then we have also glue components in terms of torque that are torque couplers. They are glue components for mechanical systems that act on the same shaft, and they can be gears, they can be planetary gear sets, or they can be clutches to engage and disengage components. Like we would maybe like to disengage the combustion engine if we're running hybrid vehicle in all electric drive, or we might want to disconnect some components from the system. And the basic equations and models are that we're keeping track of the angular velocities from geometric gear ratios, and we are looking at the torque transmission, and we're calculating the transmitted torque from the power balances. And then we add submodels for friction and gear losses or other losses. We also have power split devices that are splitting the power between different shafts. So a very often used or encountered power split device is the planetary gear that you can find in the Toyota Prius 1, and you can find it also in the Chevrolet Volt and the Opel Ampera then. They are an important component for achieving flexibility and speed matching. And the modeling approach here is to look at the speed relations and using torque transmissions from power balances. So, for example, we can have a ring gear here to connect it to a motor axle. We have the drivetrain that's connected to the planets, and then we have the sun here that's connected to generator. And with the planetary carrier and the generator sitting here, we can decouple the output axle to the engine, so that with loading on the generator we can get a decoupling between the output shaft and the input shaft. So we can get a continuously variable transmission ratio by controlling this device, so that we can optimize the engine operation to the most favorable points. Then we have the gearboxes that are more fixed. So we have the manual gearbox that most are probably aware of and have encountered. We have the automatic gearbox that has a torque converter that's often called automatic transmission. That's like the American way, the American gearboxes. Then we have the automatic gearbox with automated clutch, AMT, so automated manual transmission, where we're using a control system to control the clutch and control the gearings. This is the way Volvo and Scania truck company are using in their heavy-duty trucks. Then for some passenger cars, the dual clutch systems have been popular because they give a possibility to achieve torque. They give the possibility to transmit torque during the gear change. And then we have the CVT, which is a continuously variable transmission. When we look at the modeling for these, we have the causality from the quasi-static approach. We have the power requirement that comes from the driveline, and we transmit it to the input side, like the engine or the electric machine. And we have the gear ratio that we're controlling or selecting, or we're setting fixed, but it's used to connect the power deliveries to each other. In the dynamic approach, the torque that we get from combustion engine or electric machine is placed on the gearbox, and through the gear ratio we get that torque out, and that torque out will drive the vehicle, and the vehicle will respond, and the torque interaction between the vehicle and the losses will give the corresponding angular velocity that is transmitted in back to the engine or the electric motor. So we have power balance in the loss-free model. If we have no losses, these are directly connected to each other. And we have the gear ratio here that you can see that if we multiply omega 1 T1 and the omega 2 and T2 here, we will get the power balance of the device. When we look at more detailed models of the gearbox, it's natural to utilize a Willens-like approach, because the gearbox, when it's rotating, we will have some viscous oil elements running around all the time, and the cogs are running inside the gearbox, so they will be like a basic load, and then we will have friction in between the cogs, and the cog grippings will have a small loss. And that is modeled then with this gearbox efficiency. And in traction mode, we have this application. So this is an equation, so it works back and forth if we use QSS or if we use the dynamic approach. So it couples the equations to each other. And in the traction mode, we are taking energy from the engine side or motor side, and we're providing it to the output side. And then we have this loss here. We also have this loss that we take away. If we go the other way around and do regenerative braking or charging, we are taking energy from the output shaft side and we are using it to overcome the friction losses, and we're not able to transfer everything because there are some cog losses on the gearbox in that direction. The gear ratio that appears in the gearbox here, we can use that to test to control how efficient the vehicle will be. And there is a potential to save fuel, and there's a case study in the book, that is case study 8.1, that we will look at later. The software for running that case study is also included in the QSS toolbox that you will download. So the clutch and torque converter are sitting here, and they are decoupling the system so that we can have one rotational speed on one side and another rotational speed on the other side. And it's used, for example, during gear shifting events where we change the gear ratio here and are changing the interconnection speeds here. And for these we do the modeling in the way that when we have clutch plates and the clutch plates are touching, we have the same torque on both sides. So we have one action torque and a reaction torque. We cannot do any magical things, but these need to be the same. And that is the transmitted torque in the clutch. And the power loss that we get in the clutch will be connected to the transmitted torque times the angular velocity difference between the different sides. So how much they are slipping. So it's slip times the transferred torque that gives the power loss that can heat up the clutch or cause wear in the clutch. The characteristics of a friction clutch can look like this, where we have a high sticking torque, and then when it starts to slip, it reduces the torque. So we go into hydrodynamic effects up here when the slip becomes bigger and bigger. And when we're controlling the torque transmission in the clutch, we are using a modulation technique. So with a higher clutch force, we can scale up this point and likewise scale down this point for the braking part. So we are modulating how big torque we can transmit. So when we separate them completely, they are down here at 0. And then when we start to bring the clutch plates together again, the transmissible torque is increasing. But the general shape of this guy is like this. So this is just an equation representing what you're seeing up there. We have also the possibility to use a torque converter in automatic, in a car with an automatic gearbox. It's not so often encountered in trucks. It's sometimes used in city distribution vehicles or garbage trucks or some off-road trucks where you have a lot of changes in vehicle speed and you need to respond quickly, and that can be done then with an automatic transmission. And the modeling of an automatic transmission is done with the aid of 3 things. We have a slip here, and the slip is seen here. So 1 means that we have the same speed on the input and output side. So that's this part here. And then we have a torque loading curve that relates to the input speed. And we have the input speed here, and we have that torque loading curve that is illustrated here. That one tells how much torque we will be consuming on the input side. And when we come to the output side, so we have the slip, we have this psi here, and then we have the psi here that also depend on the slip factor. So we take this torque and we multiply it with this torque multiplication factor, and this torque multiplication factor can be up to 2 or maybe even about 2, depending on the transmission design. So that's why we have a torque increase, but it comes at a cost in terms of slip. So we need to have some slip to be able to get that torque multiplication acting. When the slip is 0, it doesn't transmit any torque. So then we need to make some, we would like to keep it here, and that is achieved by implementing a lockup clutch inside the torque converter to lock them up so that they are locked synchronously, so that we don't need to have any slip to transfer torque, so that there will be no slippage losses in the system. So when we're talking about the gear ratios, we have the connection between the gear ratio and where we end up inside the electric machine map or in the combustion engine map when we have a gearbox. So the vehicle motion equation is like this, you recognize it, and if we say that now I'm interested in seeing where we end up when we're running at constant speed, so for example, where are we ending up at 50 kilometers an hour or 70 kilometers an hour or 90 kilometers an hour? Where is that in the map? And then we say that we're running at constant speed for these cases, and then we can use the vehicle motion equation to calculate the tractive force requirement from the vehicle body. And a given speed will require a certain power from the powertrain. So if we have this power requirement from the vehicle, and when we have the given velocity, we know the power requirement that the transmission needs to provide. And that power requirement, if we neglect the losses, that needs to come from the electric machine or the combustion engine in the end. So with an ideal gearbox or a perfect gearbox, we can quickly get some impressions of where we are ending up, because these systems are usually quite well designed, and they are so well designed that it's difficult to measure the losses and the efficiencies of them. So the required tractive force increases with speed. It increases quadratically, and that means that the power requirement will increase with the cube of the speed. So if we have a fixed gear ratio, there will be an associated increase in the required engine torque. But the relation between the engine torque and the force at the wheel are quadratic to each other, but it's the power requirement that's cubic, while the engine torque requirements is quadratic. So gear ratio selection. So here we're seeing power requirement of 20 kilowatts, 10 kilowatts, 3 kilowatts. And then we can go in and look at how we end up with different gears. So we have fifth gear, we have fourth gear. And according to the simple model, the 120 kilometer hour would be lying at the same power requirement. So I don't really know what's been plotted in this, if it's just an artifact or if it's the case that can be in reality that you are using a direct drive gear. So there's one gear that has direct drive, and that gear has lower losses. So we will need, in this case then, if gear number 5 is the direct drive, it requires less power from the engine than driving at the same velocity in gear number 4. So usually you try to have a very fuel efficient gear where you're driving the most, and gear number 5 is a natural choice for many passenger cars because that is where you're spending quite some time if you're not driving only in city. So selecting the gear ratios helped us to achieve the goals. So if you're looking at this here, you see that the fourth gear is dimensioned so that we should at flat road hit the maximum power point. So we are achieving 202 kilometers an hour with the fourth gear, so we're hitting this point here with this gear ratio selection. And here when we go with torque with gear 5, we hit the torque limit before we come up to the maximum power point. So the torque is the limiting factor here, while we're hitting the sweet spot in terms of power for gear number 4. So that's why gear number 4 is usually used for top speed and for hill climbing or other things. When we select the gear ratios, we select them to optimize the fuel economy, but we're also selecting them for ease of driving, and we can have quite often a geometric ratio between the gears so that it will give get the same feeling when we switch from gear 1 to gear 2 and from gear 2 to gear 3 and gear 4, gear 3 to 4 and 4 to 5, so that we have the same feeling. We rev up the engine in the same way in between all gears. It gives a natural working with the system. Another view of the selection of gear with a road-centric view. So here we are now placing the road in the center, and we're looking at the vehicle speed, and we have the vehicle driving resistance curve here, where we have rolling resistance and we have the air drag that is added up. And at this point up here we have the maximum speed point, and we see that the maximum speed point here is achieved with gear number 5, gear number 6, gear 5, gear 4, etc. So we have the best vehicle velocity in gear number 5, while gear number 6 is in this case a fuel economy gear. And if we look at the outline shape here, we have the shape with a wide range of torque and a wide range of speed that is managed by having a gearbox. But with an electric machine that has this kind of behavior, we could match the necessary driving like here. So we would have high launch torque with only one gear, and we would have high speed with the high speed or the high dynamic behavior of the electric machine. So the electric machines can cover the operating range without gears, but with gears we can also make the placement inside where we get the operating points inside the map, so that we can tweak the operation to fit the sweet spots when we're doing the most of the driving, that we try to place in the highest efficiency regions of the electric machine. So we have looked at all the components now, so we have all the components covered, and we will in lecture number 3 talk more about definition and have a buzzword bingo about different hybrid concepts, and talk more about what this P0, P1, P2, PS, P3, P4 hybrid means. But you have now seen all the components here, so you are ready to start modeling and start to getting the equations and get parameters into them and start doing some computations. So with that, I end lecture number 2 here, to just show that we have covered all the things that we need to be analytical. And that's the thing that I like with the book, that it's quite analytical. It gives you analytical tools to analyze the components, to analyze the fuel consumption, to analyze drivability, etc. So we get an opportunity to work quite a lot with these data and with these components. So Next lecture will be on hybrid electric vehicles and the different configurations. So see you then. Bye.